So let's create another geocontainer. This will be the tree. Dive inside, and the idea here is that we manually create the trunk line, and on that we will scatter some point that we will feed into a solver to generate all the branches. So let's start with a line on the y-axis, and we want to make it, let's go to the other stuff. We will raise the tree, but let's say it will be something like this, 15 of length. And we want to resample the line, let's say with 20 segments, and we need the U attribute. So now we have 20 points, and we can apply some noise with a point VOP. So drop down a point VOP. This will be the noise, and that's it, and dive inside. So in here we want to use the U attribute to drive some noise. So basically we don't want that noise to be present on the starting point. So let's take a bind. We will read the U attribute with this one, and this will be fed into a ramp parameter. And basically we want to use a noise. Let's take an anti-aliased noise this time, and we want to feed the position, and the result of the noise will be multiplied for this ramp. So this will be a spline ramp. This is going into the multiply, and we want to add this result to the current position. So let's take the global position. This will be here, and this sum will be fed into the P. Let's reset the ramp, and if we go inside and increase the amplitude to, let's say, something like 6, you can see that basically we are restraining the noise based on the U attribute. So let's dive back inside the noise so we can tweak it. I would say 6 as the amplitude is fine, but we want to decrease the frequency, and we want to output as a 3D noise, of course. So let's say 0.2. And for the ramp, I want a B-spline and do something like this maybe. And I want to be able to change the result of the noise. So first, let's create a null. Let's call it control. And here we want to add a global seed to change the whole shape of our tree. We will tie this parameter to various other things. So edit parameter interface. Let's make this to invisible. And let's take a float parameter. Let's call it a master seed, like mseed for the name. Apply and accept. And here we want to dive inside the noise. So we can tie this to the all offset or just one axis. This is up to you. I want to tie this to the X offset. So we want to also be able to change it manually. So let's drop down a parameter. This will act as a manual slider. So offset, let's call it just offset. And let's give it a name. So offset. And we want to add this parameter that will be outside to another parameter that will be outside, but it will be a reference to the master seed. So let's promote the second input. And the sum right now is a float value, so we want to set vector component. We say the X value, so it's the component 1, and let's plug it into the offset. So by going outside, we have this that we can edit manually, and then we want to copy the master seed and paste it here, so relative reference. So now we have the manual control and also the global seed value. And let's go back into the noise VOP and maybe change this from Perlin to simplex. I like better the result. Then we want to resample again this whole thing. Let's make it 60 segment and output as a subdivision curve. So we will have a smoother result. And also we want to recompute the U value. So we again have some 0 to 1 value in a uniform way. Now we want to establish a couple of vectors for the points, one that will point along the curve and one that will be orthogonal to the first one that will represent our up vector. So let's take an orientation along curve node, and in here we want to output the y-axis as up and the tangent as direction vector. So if we create the visualizer for these two guys, and we need to make the direction one as a marker vector, and let's make it green. So we do have the two correct vectors, and we will use those vectors to initialize the direction on the branches. So from here, let's take a null. We want to make this green, and let's call it out trunk line. And don't worry if for the following minutes you will see a point wrangle here called local frame. It was from a previous version. The oriental on curve is way easier to set up, so don't worry about it. This is the final version. So from here, for the branches, let's take an object to merge. We will make this green also, and we want to take the trunk line. Now, first thing, we want to carve this line a little bit. We don't want to scatter the branches on the lower part of the trunk. So let's take a carve node, and let's carve, let's say something like this, maybe a little bit less, 2.2. Now we need the U because we will use it for a few things, but right now the U is clamped because we carved the line, so we lost the value for from the carved part. And to fix this, we want to drop down a detail wrangle, and this will be a nice trick. You can save it as a recipe, so basically you will remap any attribute you want. Basically, in this case, we want to remap the U value. So let's create a string variable. We will call this attribute name. It will be equal to CHS attribute name. So the attribute we want to rename is the U. And then let's create an integer variable. We'll call this n, and it will be equal to n points on the geometry 0, basically the amount of points we have in the line. Then we want to initialize two float attributes, the min attribute, attr, and it will be equal to 1e9, and another float variable, max attr, it will be equal to minus 1e9. And this is just a short way of defining a billion. This is basically just 1 multiplied by 10 to the 9. So basically we are initializing two float variables, one which is the minimum with a very big number, and the maximum with a very small number. Now we want to create a loop because we are in a detail wrangle, so we are not iterating by default on the points. So for int I is equal to 0, I less than n, so one iteration for each point, and I plus plus. And on each point, basically, we want to compare its U value. So let me just create the visualizer for a second. And we want to make it as a text for now. So basically right now we have the minimum value, which is 0.24. So in the loop, what we want to do first, we want to read the current U value. So float at is equal to the point function, geometry 0. The string will be the attribute name. So by changing this, we can read a different attribute, and the point number is I. And now we want to compare the current value to the minimum and maximum attribute. So the minimum attribute will be updated with the minimum value between the current minimum attribute and the attribute will be retrieving. And the same thing we want to do for the max. So copy this line, max, and we want to use the max function. So basically, for each point, it will read the U value, and if this value is less than the minimum attribute, let's say, it will replace it. So basically, if we are, let's say, on point number 0, this will check, is it lower the 1 billion value or the current attribute? Is the current attribute, then it will replace the minimum and maximum attribute. This is to say that if we output the attribute just like it is, let's say for the minimum one, just to check it, you can see that the U is still going from 1 to 0.24, but on the details, we are basically writing this minimum value. And same for the maximum. If we replace the value, you can see that it's 1 because we are carving only from the bottom. So we don't want to bind it in this way. We want to write those attributes on the point. So here we basically finish the loop and we have the correct minimum and maximum. We want to do another loop. So for this time we will make j is equal to 0, always the amount of points, so n, and this time j plus plus. And in this loop, since we now have two details attribute with the minimum and the maximum value, we just need to fit the current U value according to these minimum and maximum values. So let's create a float variable. Let's call it ratr. This will be the fit function, and we basically want to retrieve this value again. So let's take it like here, but change the letter to j. And here we want to fit it between the minimum attribute and the max attribute. And we want to fit it, let's say, for now, let's say 0, 1. So this will be the standard way, then we will change it after we save it as a recipe. And now we can't bind it like this because we are in a detail variable, so we need to set the point attribute manually with this function. And we want to set geometry 0 on the attribute name. The point number will be j, and the value to write will be this new variable we created. The mode will be set. So now if we go back on the points, we do have the U going from 0 to 1. You can see that it has correctly remapped the value. Now, if you save it as a recipe, you can reuse it as you want, giving the custom attribute name. In this case, I need the U, but I don't want to rewrite it as the U value. So we actually want to rename it to a new attribute. We will call this mass. And let's display it. So mass, we will make it as a text attribute. So 0, 1, and we don't want this range from 0 to 1. We need this mass attribute to drive basically the growth of the branch. So we want to remap this value to 1 to 0.6. So the root will start at 1 and the final point will have a 0.6 value. I made it write it from 0 to 1 with the attribute name because it's more convenient for the recipe, but I want to explicitly say mass here so I don't have to remap and refit the value I need. But of course, you're welcome also to create another string parameter for the writing attribute, incorporate some fit function with 2 parameters here. It's up to you. Now, we do have the lines, we do have the local frame, and we do have the mass value. So let's take a scatter, and now we will scatter some points into this trunk. Let's say 12 points. And we want to tie the master seed on the control to the global seed over here. So basically, if we change the seed over here, we are changing completely the shape of our tree. On the scatter, let's also crank up the relax iteration. We want a uniform distribution, at least for the main branches. And now if we template the curve, basically what I want here is also to add 2 points, 2 final points at the end of the trunk, so they will act out as our final branches. So let's take another car, or rather let's duplicate this one. And here, instead of cutting, we want to extract, but we want to raise this almost all the way up. So let's say 0.99. And we want 2 of those, so let's drop down a merge node and maybe also a transform. I don't know if we're going to move this other one, but either way. So we have 2 points here and 12 on the left side. Let's merge these guys together. Now, for the initial orientation of the branches, we need a correct point order. After the scattering, if we check the point order, it's all messed up. So after the scatter, we want to drop down a sort node, and we want to sort the point order based on the U attribute. So it will be based on the curve. So we want to go on the point sort and say by attribute and choose the U. And since we added this after in the merge node, the 2 points, also this will work because it will add the point order after the previous ones. Now, the whole idea behind the solver is that given a set of points that will act as our main branches, each time the solver will cook, we'll first recalculate the direction, the growing direction of the branches according to different things we'll implement into the solver, and then we'll move toward that direction. So even before going into the solver, we need to actually modify this initial direction, because as it is right now, they will basically grow all in the same direction. Now, if we consider the trunk as a straight line, right now the point direction is the same as the trunk direction. This is not what we want. Basically, we want to rotate this direction vector on the up one, and we want to do based on the height of the trunk, which is to say the mass attribute we stored before. And in this way, we can control the angle of spreading based on some factor, which is to say the lighter branches will fan out less compared to the lower one. And the problem, if we do it as it is right now, they will all rotate in the same direction on the same side. So before rotating the direction for the spreading effect, we actually want to rotate the up vector. And we want to do it with this 137.5 degree. This is basically the golden angle. It's called the golden angle, and it's an actual angle used by plants while growing. So basically the whole idea behind the solver and this tutorial is to take some proper botanical laws and simplify those and use it to create something nice. So basically we want to use this angle, this 137.5, and rotate the up vector on the original direction one by this angle multiplied by the point number. So this is to say point number 0 won't rotate at all. Point number 1 will rotate by this angle, so it will be something like this. Point number 2 will rotate by this angle by 2, so something like this. And this overall should give us this rotational effect as we go up with the branches. So back in Houdini, let's take a point angle, and I disabled the noise for the time being. So let's call this init attr and plug the merge. We will write different attributes on this wrangle. For now, let's just take care of the direction and the up vector. So first, let's create an integer variable. We will handle the seed with this, so chi, and we'll call this seed. Then we want to create a few float parameter, one for the golden angle. So golden, it will be equal to chf golden. And you can hard code the 137.5 VR, but it will be more practical with a slider. So then we want angle mean for the spreading out on the direction. So chf angle mean, and an angle max. So copy paste this line and let's angle max. So let's create the parameter here, and we want to tie the master seed. So copy parameter to the seed we created over here. And for now, let's leave everything as 0. And now the first rotation we want to do is the one for the up vector using the golden angle. So we need another quaternion to rotate by the golden angle on the original direction axis and update the up vector with this value. So let's create a vector 4. We will need 2 quaternion this time, so let's call this quat up, and we will use the quaternion function. The angle is the golden, but always in radians, and the axis is the original direction. So let's edit the parameter interface, look for the golden, let's set the maximum to 180. And now we can create a new vector. Let's call this new up, and we will use the qRotate function to rotate with this quad up quaternion we just created, and we want to rotate the original up vector. So if we update the up vector with this new up and write it correctly, if we increase the angle, you can see that it is rotating right now. Of course, they are rotating all the same because we are not taking into account the point number. So what we want to do actually to keep things clean, let's create another variable. Let's call this base. So the base angle will be the ptnum plus the seed. So we can use this as an offset, let's say, multiplied by the golden angle. Golden. And now let's replace the base here. So now, as you can see, we are creating this sort of spiral effect. So if we set this to 137.5, we do have something like this. The only minor thing I want to add to this is right now they are all rotating exactly this angle. So maybe we want to add a little bit of perturbation, let's say 10 degrees less or more than the golden angle. So after this, let's compute another variable. Let's call it pert, and it will be equal to the random on the ptnum minus 0.5 by another channel. We will call this CHF pert range. And if we click here and set it to 20, basically this pert variable will be equal to minus 10 to 10, because this will output a value between negative 0.5 and 0.5, and we are multiplying by 20. So after this, let's define a final angle. So it will be clean float up angle. It will be equal to the base plus the perturbation range, and here we want to use the final up angle. So basically we are adding a little bit of noise over here. Let's say 20 is fine. And now we need to rotate the direction vector. So let's temporarily set the golden angle to 0 and also the perturbation range. And here let's create another variable for the direction angle. So dir angle, and here we just basically want to fit the current mass, so f at mass, which is going from 1 to 0.6, and we want to fit it from angle min and angle max. After the vector, let's create another quaternion. We need this one for the direction, so quat dir quaternion function in radians, and this time we want to use the direction angle, and we want to rotate on the new up, not the old one, so new up. And what's the problem here? We need another parenthesis. No. Oh, we need to use a fit 0, 1, because we are giving only 3 arguments and we don't need the additional parentheses. And finally, vector new dir, it will be equal to qRotate the quat dir, and the vector we want to rotate is the direction one. Then we bind it, so v at dir is equal to new dir. And if we increase the angle max to, let's say, 80, you can see that is working but not correctly. Let's see what's wrong here. We do have mass. Oh, right. We actually need to calculate the mass. So let's rename this one here. And after we want to do the extraction for the final point and the scattering. So if we set it on the side view, you can see that we're going from 80 degrees to not 0 because here the mass is 0.6 and we are actually clamping this time some value, but this is fine because I don't want to set this to 0. This I want to set to something like 45, 30, so maybe even something like this, but I will leave it as 0 for now. So let's see how it goes, and let's reset this value to the proper golden angle and reintroduce the perturbation range. So finally, let's visualize also the app. Now we have some proper initial vector. Now the final thing would to be put these points into a group. Let's call this group like moving and set it to point. Basically, we will apply the operation inside the solver only to the moving points because we will also generate the trail inside the solver. So now we are ready to deal with the whole solver stuff.